down or taking a picture of them. I think that'd be very wise. I mean, think about it. If you were in class, I would be writing these down on the board and demonstrating these, and I would probably stress that, you know, we need to try to get these down so we have something to look at, something to go off of when we try to do our textbook homework and or quizzes or future exams. So it's very important that we, you know, document this, even if we don't understand it 100% at this point in time. At least get it down so that after class, when you can slow the pace down, you can then begin to go back through the steps and try to reconcile what just occurred in class. Okay, very important. All right, so do we have this page accounted for here? We're good on this? Okay.
Yeah.
All right, so I will leave that behind. All right, so that's called the grouping method, ladies and gentlemen. It works for 4-term polynomials, usually. Now we're going to look at the trinomial family. Trinomials, factoring trinomials. Of course, trinomials are 3-term variable or algebraic expressions. Tri means 3. Let's start off by factoring some simple ones first. How about this one? X squared plus 5x plus 6. Okay. All right. Now, this is a trinomial. In fact, this trinomial happens to be a quadratic form trinomial, since the leading degree, 2, is twice the degree of the middle term. We call this a quadratic type of trinomial, if you will. If these can factor, they always factor into the product of 2 binomials. Furthermore, this trinomial is called an easy type of trinomial to factor because it has a leading coefficient of 1. Factoring these is pretty simple. All we need to do, ladies and gentlemen, in order to factor these types of trinomials is we come over to our constant term, which is just plus 6 at the end here. And we need to find 2 factors of positive 6 that add up or sum up to give us our middle coefficient, which is plus 5. Now I'm going to list factors of 6, 1 and 6, -1 and -6, -2 and -3, and 2 and positive 3. In this list, there's 2 factors that add up to positive 5. Which ones are they?
2 and 3.
2 and 3.
Yeah, the only ones that work are 2 and 3. None of these other ones will sum up to positive 5. So in order to factor this trinomial now, we can immediately factor it into the product of 2 binomials. The first terms of which have to be x, because think about it. If you want to check your answer and FOIL this out, x times x has to give you back the x squared. The last terms of these binomials are going to come from our decision of our factors of 6 over here, which was to say plus 2 and plus 3. Or you could have these switched. You could have the x plus 3 here and the x plus 2 here. Does that make sense? This would be the correct factorization of that trinomial.
Yes.
If you were to FOIL this out, multiply it all out, gather together your 2 middle like terms, you would get back this trinomial. Do we remember how to factor these? Have we ever factored easy types of trinomials like this before? Do you remember?
Yeah.
Yes.
All right, maybe we can try another one like that. All right, let's see here. How about, let's say p squared plus 5p minus 66. Okay, we want to factor this trinomial. Again, it's a quadratic form or quadratic type trinomial because this degree is twice the middle. It has a leading coefficient of 1, so it's an easy type to factor. We need to find 2 factors of -66, the constant term, that add up to positive 5. Now, if you can't think of it, or it doesn't, those don't pop into your mind later on, you might have to climb the ladder and listing all factors of the constant term. And in some cases, the list may be quite long. Okay. Okay. I mean, notice that we do have quite a list here, correct? 4 don't go into 66 evenly, 5 don't, 6 does, -6 and 11, or 6 and -11. 7 don't divide into 66 evenly, 8 don't, 9 doesn't, 10 doesn't, 11 does, and we're done. So in this list, ladies and gentlemen, which ones add up to 5?
11 and -6.
Now, these are the only ones, after inspecting these factors of 66 in this list, the only ones that sum up to positive 5 are -6 and 11. Those are the only ones, you know, that add up to our middle coefficient. Because of this, this trinomial now immediately factors into p minus 6 times p plus 11. And we're done. or you could have these switched around. You could have the p plus 11 times the p minus 6 here. Okay. Factoring easy types of trinomials. Does that ring a bell, ladies and gentlemen? Okay, hopefully you've done those before. I mean, you really should have done trinomials of this caliber before. I mean, if you've never, ever, ever factored a trinomial of this type ever before in your life, you are seriously in the wrong class. You really are. Okay, these make sense so far here, ladies and gentlemen?
Yeah.
Yes.
Okay,
Yes.
those are the easy types of trinomials, but we have some that are the difficult types too. All right, let's try this one. Let's try to factor, here we go, 2t squared minus t minus 15. We want to factor this trinomial here. All right, notice it is a quadratic form trinomial. This degree is twice this. But unfortunately, unlike the other ones, we don't have a leading coefficient of 1 anymore. We have some other number. Factoring these types of trinomials is more difficult than factoring the ones where the leading coefficient is 1. There's two main schools of thought for factoring these types. You can use a trial and error or guess and check method, or ladies and gentlemen, you can use a more systematic approach called the grouping method. In all the years that I've been teaching these trinomials, I still always lean towards the grouping method because it minimizes the amount of trial and error and guesswork. The other method is nothing but trial and error. But listen, if you're used to factoring using your guess and check or trial and error method, I'm not going to prevent you from doing that. By all means, factor them that way. I have nothing against that. Okay, the bottom line is we got to get this factored. All right, but I am going to demonstrate the grouping method. If you've never seen it, hey, take it in. You might fall in love with it. It really is a neat systematic technique for grouping these difficult trinomials here. Here's how the grouping method begins. So it is called the grouping method. We kick off the grouping method here for factoring this difficult trinomial by multiplying the leading coefficient and the constant term. So I'm going to take the 2 and multiply it by the negative 15. That gives me negative 30. Now we're going to have to search for a couple of factors of negative 30 here that sum up to our middle coefficient. Oh no, what is my middle coefficient?
-1.
Yeah, I don't see anything here. It's just negative t, but it's understood it's negative 1t, understood. So I need two factors of negative 30 that sum up to negative 1. Can you think of what those two factors might be? Or maybe
-6 and 5.
yeah, after a little thought, or if you can't think of these, you're gonna have to list them all out and then decide. But most of the time they pop into your mind, okay? So -6 and 5 are the only factors of negative 30 that do indeed, add up to our middle coefficient of negative 1 right here. So this is the only combination of factors of negative 30 that's gonna work. What we do now is we rewrite our trinomial, our difficult trinomial, as an equivalent 4-term polynomial, where the middle term gets split up and rewritten as the sum of our decided upon factors over here. So negative 1t is going to be rewritten as negative 6t plus 5t. Or, ladies and gentlemen, you could have these switched. You could have plus 5t here and minus 6t here. It doesn't matter what order. Do you agree that this 4-term polynomial is equal to my original trinomial?
Yes.
Okay, now how do we factor a 4-term polynomial? We use what technique? The grouping method. And that's why this overall procedure is called the grouping method. So we group together our first two terms and our last two terms. No sign adjustment on the last term here necessary. What can I factor out of the first two terms here?
2t.
I can pull out a 2t times what would you leave behind?
T.
Is 3. Plus, what can I factor out of 5t and 15? 5 times, we better leave behind the t minus 3, do we?
Yep.
Looks good. Now, ladies and gentlemen, we pull out the common binomial factor of t minus 3 times, what do we leave behind in doing that?
2t plus
2t plus 5. Ladies and gentlemen, we have factored that difficult trinomial. It's called the grouping method. Have you ever seen that method or worked with that method?
yes.
Okay. Again, if you just want to, factor this trinomial using your guess and check or trial and error method, I don't have anything against that. As long as, we can all get this factored correctly, I am happy. Okay. Of course, if you were to FOIL it out, you would get this back. All right. So that's how you factor, let's see, the difficult trinomial. Any questions on that? How the grouping method worked on that one? Okay. All right. Okay, let's try to factor this here. 2t cubed minus 28t squared plus 80t. All right. We want to factor this trinomial. Now, what was that first question we always ask ourselves? What did I open up with that first question?
What can we take out?
That's right. Always try to ask yourself, remember to ask yourself, what can I factor any greatest common factor out of all the terms first? Because if you can, you need to do that first. I don't care what your polynomial looks like, always entertain that first thing there. Notice up here, we were not able to factor anything out of 2t squared minus t and minus 15. For that reason, we had to use the grouping method to factor that trinomial. But down here, ladies and gentlemen, what can we factor out of all three terms? Anything other than 1 or -1?
2t.
Now you can pull a 2 out and also a what? A t out. You need to do that first. And when you do that, what do you leave behind?
T squared.
T plus 40, correct? 40. All right. Now, before we call it quits, ladies and gentlemen, we need to make sure this polynomial is completely factored. We need to go inside the parentheses here and ask ourselves, can this trinomial we leave behind itself be further factored down? Fortunately, it's an easy type, one with a leading coefficient of 1. So to see if it is factorable, we come over to the 40, the constant term, and we ask ourselves, are there two factors of positive 40 that add up or sum up to -14? Do they exist? After a little thought, -4 and -10 are factors of positive 40 that add up to what? -14. Because of that, this trinomial is going to what? Factor. And therefore, it would factor into what two binomials?
T minus 4 times T minus 10.
T minus 4 times T minus 10. Ladies and gentlemen, this trinomial has been factored. Notice we cannot further factor down any of these three remaining factors. And so this is called the complete factorization of what we started with up here. That's the complete factorization. So again, I cannot emphasize enough, when you're staring at any sort of polynomial, always try to factor something out of all the terms first, because if you can, you always do that first. If you can't, you can, but if you can, you need to do that. If you were to take the time and multiply this all back out, gather together like terms, you would get back this original polynomial, okay? Any questions about that one? All right, ladies and gentlemen, the binomial family. Binomials. Bi means how many term variable expressions?
2.
2 terms. So let's look at the binomial family, how to factor binomials. All right, ladies and gentlemen, there are 4 binomials that we have to be concerned with as far as factoring is concerned. The first one is called the sum of perfect squares, or the sum of squares. A squared plus B squared is a binomial. It's a 2-term variable expression. Notice we have the sum of 2 squares, the sum of perfect squares. Can we factor the sum of perfect squares? Anybody want to weigh in on that? Could this be factored? Anybody remember?
It can.
What's that? It can or cannot? Okay, I think I heard the word cannot. You are right. Ladies and gentlemen, the sum of perfect squares is always non-factorable. You cannot factor it over real numbers. Okay, you can over complex numbers, but not real numbers. So we say it's non-factorable. All right. Now, somebody's probably saying, and I know there's a lot of temptation out there having us think that a squared plus b squared would factor into a plus b squared. I mean, what's the point of that? Why wouldn't it do that? Well, if you were to take a plus b and multiply it by itself, would you get back a squared plus b squared? Well, a times a gives you back a squared. A times b gives you back plus ab. B times a gives you back another ba or plus ab. And b times b gives you back b squared. The problem is these two middle terms do not drop out of the picture. They actually add up. And so, you can clearly see that a squared plus b squared just does not factor into a plus b squared. Doesn't work. No good. So you cannot factor the sum of squares. Doesn't work. All right. All right, that's the sum of squares. Now, how about the difference of squares? The difference of perfect squares. If like you have a squared minus b squared. This is called the difference between two squares. Can it be factored? And if so, how? How does it factor? Anybody remember this? How this factors? Well, as it turns out, the difference between two squares does factor, and it does factor into the product of two binomials, and these binomials are actually called conjugates of each other. Does that ring a bell, ladies and gentlemen? You ever seen this factorization for the difference of squares?
Yes.
Yes.
All right, these binomials are called conjugates of one another because they differ only by the sign in between the terms. So you can always factor the difference between perfect squares, and it always factors into the product of conjugate binomials. If you were to multiply these out, a times a gives you back a squared. A times a negative b would be a negative ab. B times a would give you plus ab. What happens to these two middle terms then?
They cancel
That's
They
out.
would drop. They drop out to zero, and b times negative b is minus b squared. So yeah, I mean, the difference of squares does factor into, oops, hold on a second. Does factor into the product of those conjugate binomials there. How do you even determine if you have like a perfect square, especially when it comes to a number? Well, like if I give you the number like 144, ladies, I mean, how would you even know if 144 is a perfect square? Well, on your TI-84 calculator, you can take the square root of this. Okay. Now, where's the square root function on a TI-84 calculator? Well, it hangs out above the x squared button. So you'd have to hit your second key. Then you'd have to hit your x squared button, because above your x squared button is your square root function. Then you have to type in 144. I think you have to type in a closed parenthesis, maybe or maybe not. And then hit enter. And what would you get if you take the square root of 144? You would get 12, correct? Because
Yeah.
144 is 12 squared, or 12 times 12. All right. So that's how you can determine if a number is a perfect square. Just take the square root of it on your calculator, right? Using your TI-84 there. Okay, so what I've shown you so far is two binomials: sum of squares, which never factors; difference of squares, which always factors into the product of conjugate binomials. There's two other binomials that we need to concern ourselves with. The next one is called the sum of cubes. The sum of perfect cubes, a cubed plus b cubed. Can we factor the sum of two cubes? And the answer is yes, we can. And it always factors into the product of a binomial that looks like this and a trinomial that looks like this. Wait a minute, this should be a plus. Hold on a second. And this should be a minus. Okay, so it factors into a plus b times a squared minus ab plus b squared. That's how the sum of cubes always factors. Can we factor the difference between cubes? Difference of two cubes. And the answer is yes, we can. It factors in a very similar way that the sum of cubes factor. The only difference is the signs get switched around a little bit. Here would be a minus b times the trinomial a squared plus ab plus b squared. There, ladies and gentlemen, shows you how you can factor the sum of cubes and the difference of cubes. How would you even know if a number qualifies as being a perfect cube? Like 64, is that a perfect cube? Well, you would find out if you take the cubed root of it on your TI-84. How do you take a cubed root of a number on the calculator? Does anybody know? What's that?
Yeah, you hit the math button and then it's option number 4.
Let me bring up my, hold on a second here. Let me bring up my calculator here. So there is a cubed root function on your calculator. Ladies and gentlemen, or if you don't have a cubed root function on your calculator, you just raise the number to the 1/3 power. Right? If you raise the number to the 1/3 power, that's like taking the cube root of it. Okay, so my calculator is having a, it doesn't want to cooperate on Monday here. So, yeah, so, I don't know what's going on. So anyways, it is in your math menu, ladies and gentlemen. If you hit your math button on your calculator, and then you go down and you grab, there's a cubed root function. You see that? Math, go down and get the cubed root function, type in 64, hit enter, and what do you get? You would get 4. Because 4 to the 3rd power is 64. 4 times 4 times 4 is 64. Okay. We all see that function on our calculator? Okay, I'm assuming we do. All right, so let's factor some binomials. 16t to the t squared minus 49. Ladies and gentlemen, how would that factor, or does it factor? Is this the difference of squares? Well, 16t squared, after a little thought, is 4t squared. 49, if you take the square root of 49, you get what? 7. So it's a perfect square of 7. And you can clearly see that we have the difference of squares. And so therefore, since we have the difference of squares, it would factor into the product of conjugate binomials. Our A is really like a 4t and our B is like a 7. So we replace A with 4t, replace B with 7, we got it. So this factors into 4t plus 7 times 4t minus 7. Does that make sense how we factor that difference of squares in? We would factor like this. Questions on that one? All right, how about t to the 4th power minus 81? Can this be factored? Might it be the difference between squares? Well, t to the 4th power is the square of what? T squared?
Yeah.
81 is a perfect square of 9. So you can see that we do have the difference between two squares. My A is really like a t squared. My B is like a 9. So following this pattern here, I would have t squared plus 9 times t squared minus 9. But ladies and gentlemen, can any of these factors themselves be further factored down? We need to at least check. T squared plus 9 is the sum of squares, which cannot be further factored down. However, t squared minus 9 is itself the difference between squares, 9 being a perfect square of 3. So this needs to further factor down into t plus 3 times t what? Minus 3? And that would be your complete factorization of t to the 4th minus 81. That's your complete factorization of t to the 4th minus 81. Is this bringing back memories, ladies and gentlemen? Factoring difference of squares.
Yes.
All right. X plus y squared minus z squared. Now they're going to give you a different look. I notice your book is famous for giving you oddball type of problems, ladies and gentlemen. So gone are the days of elementary algebra when you would do like maybe 30 of these type of problems only. Your book shifts gears, problem to problem to problem. Every problem is radically different in your sections, I've been noticing. Welcome to the world of college algebra. All right, so ladies and gentlemen, how do we factor this? Might it be the difference between, might it be the difference between two squares? You can see that it is the difference between perfect squares. So it does factor. And it factors into what? Conjugate binomials. The first terms of which have to be what? X plus y, because x plus y squared is the first term in my difference of squares. So I must have an x plus y here and an x plus y here. The last terms have to be z, because z squared is the last term of my difference of squares. So I will have a plus z here and I'll have a minus z here. Ladies and gentlemen, this is the factorization of that difference of squares. Kind of strange, isn't it? But that's how it would factor. Maybe it'll help you to see it better if you can close those in parentheses, right? X plus y times itself, x plus y squared, z times negative z minus z squared. That's how it factors. Any question about factoring the difference of squares? All right, let's try this one. How about x cubed minus 27? Does this binomial factor? Is it maybe the difference of squares or maybe not? Maybe the difference of not squares, but
Cubes.
cubes? Is 27 a perfect cube? If on your calculator you take the cube root of 27, you'll discover it's a perfect cube of 3. And so, ladies and gentlemen, x cubed minus 27 can be rewritten as x cubed minus 3 cubed. Hence, following along with the pattern of the difference of cubes, this is the pattern, how you factor in general the difference of cubes. Our A is really a what? X, and our B is really a 3. So wherever we see an A in this pattern, we replace it with an X and replace B with 3 everywhere. So we're going to have X minus 3 times X squared plus 3X plus 3 squared, which is 9. Ladies and gentlemen, this is the correct factorization of this x cubed minus 27. It factors into this difference of cubes. Do we see how this is working for difference of cubes?
Yes.
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 All right. Got agreement from all different age groups here. All right. Okay. And of course, if I had x cubed plus 27, this would not be the difference of cubes, it would be the sum of cubes. So it would factor. It would factor into not x minus 3, but what? X plus 3 times x squared. Not plus 3x, but minus 3x plus 9. This is how the sum of these cubes would factor into this. Notice the only difference is the signs are just different between the sum and the difference of cubes. Notice the difference in the patterns here. Okay. All right. So we got that. That's great. Now, ladies and gentlemen, I have a question. Anybody in here going to go onwards in mathematics and maybe eventually take some calculus?
Yes.
All right. Well, these next problems are right in line with what you're going to be doing in calculus from time to time. So this is very important here. Okay, suppose I wanted you to try to factor something like this. 5 times t to the negative 7th power plus 2 times t to the negative 6th power plus t to the negative 5th power. Suppose I wanted you to factor this. All right, ladies and gentlemen, remember when it comes to, well, as far as the coefficients are concerned, 5, 2, and 1, the only thing we can factor out of 5, 2, and 1 is just 1 or negative 1. How about the variables t? What's the smallest exponent of negative 7, negative 6, or negative 5?
-5.
No, the smallest exponent of negative 7, negative 6, or negative 5.
-7.
Yeah, negative 7. So ladies and gentlemen, we're going to factor out the smallest power on t, which is negative 7th power. So we're going to factor t to the negative 7th power out of each of these 3 terms. And when we do so, what do we leave behind? When you factor t to the negative 7th out of 5, t to the negative 7th, do you agree that t to the negative 7th reduced to 1, you're left with 5?
Yes.
When you factor t to the negative 7th power out of t to the negative 6th power, what do you do with the exponents when you divide like bases? You subtract the exponents?
Mm-hmm. So it'd be,
So I'm going to do this over here so we can see it. So that would be t to the negative 6 subtract the negative 7 power, which is really t to the negative 6 plus 7 power, which is really what? T to the first power? Everybody see that there? So when you factor t to the negative 7th out of this middle term, you'll leave behind 2t to the first power. That's it. Look, here's how you can check your answer. If you take t to the negative 7th and multiply it back by t, do you get t to the negative 6? When you multiply like bases, you add exponents. Negative 7 plus 1 is negative 6. Looks like it works, correct?
mhm.
All right, when I factor t to the negative 7th out of t to the negative 5, what do I leave behind?
T to the second power.
Yeah, negative see, -5 subtract a -7 is -5 plus 7, which is 2. So you leave behind t to the second power.
Okay, would it still be a T if you pull the T out?
What's that?
Would it still be a T if you pulled the T out?
Okay, I can barely hear. I hear part of what you're saying, Tony, but then it gets lost.
She's asking if it would still be a T even though you pull the T out with the -7.
Oh, yeah, because look at t to the -5 power divided by t to the -7 power is going to be t to the -5 subtract -7 power, which is t to the -5 plus 7 power, right?
Yeah, I
Which
get
is
that.
t what? T squared?
Yeah, I get the square part. But
Okay,
you factor the T out.
you would have t squared there. And, you know, normally we don't like to leave negative exponents appearing in our final result. So this t raised to the -7th power should come down in the denominator. And I would like to write my trinomial in what's called descending order. So I'm going to rearrange these terms so it's in descending order. T squared plus 2t plus 5. And I'm going to place this over t to the what power?
-7th.
But when it comes
The seventh.
downstairs, it's then to the
Which is-
what? +7.
Oh,
isn't it?
okay.
And there you go, Liz. I'll not do your answer. You see what just happened with that one there? This is a common thing that's done in calculus, is factoring out the smallest negative exponent out of each of the terms. It happens all the time. Okay, so that's a common thing you do in calculus all the time when simplifying your answer down to your final result. All right, we're almost to classwork number 1. X times 5x minus 8 to the -4/5 power plus 5x minus 8 raised to the 1/5 power. And we want to factor this. What's the smallest exponent of 5x minus 8, since that's a common factor between both these terms here? Smallest exponent on 5x minus 8 is what? -4/5 or 1/5?
-4/5.
But we're going to factor out 5x minus 8 to the -4/5 power. And when I do so, what do I leave behind? When you pull this out of the first term, you leave behind just what? X? Because we factored this whole thing out of here, right? So we leave behind X. But when I factor 5x minus 8 to the -4/5 power out of 5x minus 8 to the 1/5 power, what do I leave behind?
The 1/5 power.
Okay. You know, if you're having a hard time seeing that, bring it off to the side of your paper here and take care of it over here. So I'm dividing this, I'm dividing out or factoring out 5x minus 8 to the -4/5 power. Now, when you divide like bases, you subtract exponents. So this is going to be 5x minus 8 raised to the 1/5 subtract -4/5 power, which is to say 5x minus 8 raised to the 1/5 plus 4/5. But what's 1/5 plus 4/5?
1 whole.
5/5. But what's another name for 5/5?
1 whole.
1 whole. So ladies and gentlemen, you're going to leave behind 5x minus 8 to the 1 power when you factor 5x minus 8 to the -4/5 out of this last term. If you don't believe me, if you multiply this back in by this base here, you would add the exponents. -4/5 plus 5/5 would give you back 1/5. We can end this problem here by simplifying inside the brackets, combining like terms. And x plus 5x combined to give you what? 6x? One last thing to do is get rid of the negative exponent on this base of 5x minus 8. So we'll flip it down into the denominator. In which case we'll have 5x plus 8. Okay, hold on. My pen just died. Yeah, get another pen. So what we're going to have then is we'll have downstairs, we'll have 5x. (5x minus 8 rather, right? Minus 8 to what power? 4/5 power?
Yep.
And that'd be your final answer. That's all you can do with that, okay? So we'd call it quits there. Okay, so factoring out the smallest negative exponent, that's something that's commonly done, like I said, all the time in calculus, and you'll be doing that again when you get into calc, okay? Any questions about this? Okay. Got this accounted for, everybody, one way or another? All right, classwork number one, ladies and gentlemen. Of course, in your subject line of your email, you're going to put math. Usually you leave a space here, math 130. Make sure you put that in your subject line of your email. And this is, after that, you can just say classwork September 13th. Please make sure you email this to me by midnight. I would like you to try a couple of these problems. I want you to factor these polynomials completely. First one, the first one is going to be 30 z cubed minus 35 z squared minus 24z. Make sure you put a slash through your z's. They can look like 2's plus 28. Completely factor that one. Then try this one, d to the 4th power minus 8d. Problem number 3, y squared plus 2 squared plus 5 times y squared plus 2 minus 24. Make sure you completely factor number 3. And problem number 4, last one. See if you can factor y to the negative 2 power minus y to the negative 3 power minus 12y to the negative 4th power. All right, there you go, ladies. On 4 problems. See if you can do something with them, and we'll come back and take a look at those. Of number 1 there. That's a complete factorization. All right, number 2. Anybody want to take a guess or a stab at this? Hopefully not just a guess.
I have d times d minus 2 times d squared minus 2d minus 4.
Okay. All right. Anybody get that? D times d minus 2 times d squared minus 2d minus 4. I did. All right. You got that also. Anybody get anything different?
I have d minus 2 times d to the 2nd plus 2d plus 4.
Plus 4. Okay. All right. Let's take a look here. Well, again, ladies, I'm going to always ask yourself, can you factor anything out initially out of all the terms? And notice we can pull the d out first. You need to factor the d out first, leaving d times d cubed minus 8. And notice that d cubed minus 8, as it turns out, is the difference between what? Cubes. Okay. Now, do you remember how the difference of cubes factors? In general, a cubed minus b cubed, it factors into a minus b times a squared plus ab plus b squared. Okay, in general. So our a here is really a d, and our b is really a 2, because so our a is a d and our b is a 2. So when you drop the numbers in where they belong, ladies and gentlemen, it looks like the final complete factorization of this thing is going to be d times d minus 2 times d squared right here, d squared plus 2d plus what? 2 squared or plus 4. Okay, so I think somebody had a minus signs here and here.
Yeah.
Do we see the little discrepancy here? Okay, you know, the key is to factoring binomials, you want to memorize all the patterns, seriously. So you want to commit the memory, Liz, on all the patterns for the sum and difference of cubes here. So I cannot emphasize enough how important it is just to memorize this pattern, okay, and to what? Memorize this pattern, memorize these. That'll take you a long way when you go onwards from college algebra, okay? Just memorize them. All right, number 3 was a challenging problem. Anybody feel confident enough to give us what you got, for better or for worse? Anybody do anything with that? Don't feel bad if you didn't get it. It's a little bit more challenging. Anybody get that factored there? Now, ladies and gentlemen, one way to factor this, which is a nasty way, by the way, one way to factor this is to completely FOIL this out, multiply this out, gather together like terms, and then factor it from there. but that is a lot of work. That's a ton of work. All right. What we want to do here is get back and look at the forest for the trees. Do you agree we got a y squared plus 2 squared and we got a y squared plus 2 to the what? First power? So in general, it's kind of like we have a big old trinomial here. 1, 2, 3 terms, where the first term is square and it's twice the degree of the middle term. So it is quadratic in form. Do you remember, ladies and gentlemen, back in intermediate algebra, ever using what's called a U substitution? U substitutions are used a lot in calculus. What if I let u, the variable u, be equal to y squared plus 2? Suppose I let u be equal to y squared plus 2. That's called a U substitution. If I do that, then I will replace this with u, replace this with u, and you know what my polynomial is going to look like then? It's going to look like u squared plus 5u minus 24. Everybody see that there? After having made this u substitution. Now look at this trinomial, looks a lot nicer than the initial mess we had. So how do we factor this easy type of trinomial? All we need are 2 factors of negative 24 to sum up to 5, and they would be 8 and what, negative 3? And so this trinomial in the variable u would factor into u plus 8 times u minus 3. Isn't that true? This trinomial factors into the product of these binomials. And now we will back substitute what we let u be equal to. Remember, u was set equal to y squared plus 2. So we will bring that back, ladies and gentlemen, and replace u here with y squared plus 2, replace u here with y squared plus 2, and then we have our binomial factors looking like this. Now we can combine like terms here. 2 plus 8 gives us 10, 2 minus 3 gives us minus 1, and we got our binomial factors that look like this. Y squared plus 10 cannot be further factored down, but look at y squared minus 1 is the difference between squares. So we can factor down into the product of y plus 1 and y minus 1. And ladies and gentlemen, this is the complete factorization of what we started with up there. You know what turned this nasty looking polynomial into one that's more recognizable? Something called a U substitution, ladies and gentlemen. U substitutions are employed all the time in calculus when differentiating or integrating an expression, because they help you see the forest for the trees. This is the trees. Difficult to see what's going on here. When you do a U substitution, this trinomial looks so much simpler looking now. You see that? That's the point of U substitutions, is to take a nasty situation, very complicated situation, and turn it into one that's much more recognizable, much more trivial to understand. Okay? Just make sure you maybe account for that problem, for better or for worse, ladies and gentlemen. There it is. That was a challenging problem. But the U substitution really would be the way to go here. I mean, you can multiply this all out and then factor it. That would be a long, unnecessary amount of work. U substitution is the way to go here. Okay, any other questions on that one there? All right, number 4. Anybody feel confident in factoring number 4? Okay. Is it Tony? I hear you a little bit, Tony. I don't know what it is. I don't know if it's my end or your end or what's going on, but whenever you speak up, it's like, it's very faint for one thing, very faint. And I don't know, it just sounds like it's coming kind of like from a tunnel or something. Can anybody hear Tony well? Anybody in the class?
I can't really.
Can anybody hear Tony well? Can you put it back up there for a second? Yes. Yeah, there. Number 3, we have another request just to see that a little bit longer there. Okay, employed a U substitution. U substitution was to the rescue there. It turned a nasty situation into one that was much nicer to deal with. Okay, used all the time in calculus. U substitutions. All right, is that good? Enough time for that one? Is that good there? Okay, we're good there. All right, number 4, ladies and gentlemen, what's the smallest power of y we can factor out?
-4.
-4.
Y to the -4. Yeah, you want to factor y to the -4 out of all 3 terms, being the smallest exponent of those. And when you factor it out, what will you leave behind? Well, when you factor y to the -4 out of y to the -2, you leave behind y squared. When you factor y to the -4 out of y to the -3, you leave behind y to the first. When you factor y to the -4th out of 12y to the -4th, you leave behind this -12 here. Notice this trinomial, however, left behind inside the brackets can itself be further factored. Two factors of -12 to sum up to -1, the middle coefficient are -4 and 3. So this trinomial further factors down into y minus 4 times y plus 3. This y minus 4, we want to kick it down into the denominator, do away with the negative sign and the exponent, and that would be our final answer. I'm just curious, did anybody get that for a final answer? Anybody at all?
I was one step away.
Okay, so you were close. All right, that's awesome. Yeah, I mean, that's not bad. If you're only one step away, at least you're moving in the right direction. All right, so that's the end of that one there. Okay, and now we got to leave that section behind, ladies and gentlemen. One last section, R6 is involving rational expressions and radical operations, okay? Rational expressions and radical operations. All right, can I get rid of this number 4 here? You got that? We good? Okay, last section in chapter R. This is R6. There is no R7. I had that on the syllabus mistakenly. All right, so let's go dealing with rational expressions. Rational expressions are when you have a polynomial over a polynomial. First thing that we normally like to do with rational expressions is reduce them. That's normally how we open up with these things in earlier algebra. So if I have like y squared minus 64 over y squared minus 7y minus 8, and I want you to reduce this rational expression here. So a rational expression is just kind of like a fraction. We have a polynomial sitting over a polynomial. All right. Before we reduce this rational expression down, you need to completely factor your numerators and your denominators. That's the first requirement. So ladies and gentlemen, how can we factor y squared minus 64? You recognize what type it is. Y squared minus 64. What do we got here?
Square.
Difference between perfect what? Squares, because 64 is a perfect square of a whole number 8. So y squared minus 64 factors immediately into y plus 8 times its conjugate binomial factor, which is y minus 8. That numerator has been completely factored. True? All right, how about the denominator? Can we factor this trinomial? Notice there's nothing we can pull out of all 3 terms except 1 or -1. Easy type of trinomial. We need 2 factors of -8 that sum up to -7. What would they be?
-8. I mean, -7 and 1.
Well, -8 and what? +1, correct?
Yeah.
Is that what you meant? -8 and +1? These are the only ones that add up to what are -7 there. Okay. So therefore, this trinomial immediately factors into the product of what 2 binomials. We would have y minus 8 times y plus 1. Ladies and gentlemen, would there be any restrictions we would have to place on the variable y such that this would be defined? This rational expressions, restrictions? Because we have a fraction, we are always concerned when the denominator of a fraction becomes what? 0, because that's always undefined. So what kind of restrictions would we have to place on y? We got to make sure that y minus 8 is never what? Equal to 0. And we got to make sure that y plus 1 is never what? Equal to 0. Because if they are, this whole thing becomes undefined. Well, when we solve this for y, we add 8 to both sides. That would imply that y can never be equal to 8. And when we solve this one by subtracting 1 from both sides, y cannot be equal to what? -1. These are restrictions that you would have to place on this rational expression here so that it will be defined. So if y is ever equal to 8 or -1, this whole rational expression is undefined. Undefined. Any questions about that problem, how we reduced it and placed restrictions on our variable? These restrictions become much more important when you start solving what are called rational equations, okay? All right, so we showed you how to reduce a rational expression. Do you remember doing this in earlier algebra, reducing rational expressions? Bring back memories? Hopefully. You remember how to multiply rational expressions, ladies and gentlemen? If I have 8x minus 3y sitting over x cubed y to the fourth, and I want to multiply this by 6xy to the eighth, and that sits over 24x minus 9y. You remember how to multiply rational expressions. First, we have to completely factor all of our numerators and our denominators. So we want to do that first. Notice there's nothing we can factor out of both these terms, and there's nothing we can do to factor it. So just bring it along. It already is factored. X cubed y to the fourth, not really much going on here. It's just a monomial, so we'll just bring it along. 6xy to the eighth, not really much going on with this either. It's just a monomial. We'll just bring it along. What can I factor out of both these terms, though, down here?
A 3?
Let's pull out a 3, and we'll leave behind 8x minus 3y. True?
Yes.
What cross cancels? Can we do any cross canceling here, or any reducing?
Yeah.
8x and 3y.
Yeah, the 8x minus 3 is cross reduce out. Cross cancel out, leave behind ones. They're gone. And what we're left with is 1 times this monomial. And that sits over this monomial times 3. Ladies and gentlemen, can we further reduce this monomial over this monomial?
Yes.
Remember, when you divide like bases, you subtract exponents. So 6 divided by 3 reduces down to 2. What's x to the first power divided by x cubed?
2x squared. Yeah, x squared.
It'll be x to the 1 subtract 3 power, or x to the negative 2 power.
Yeah.
Y to the 8th power divided by y to the 4th power is y to the 8 minus 4 power, y to the 4th power. One last move is to do away with this negative 2 exponent. How do we do that?
Put it under
Yeah, just
the
flip
bottom
the-
side of a fraction.
Exactly. Flip the x downstairs and call it x to the positive 2. Make sense, ladies and gentlemen? That's your answer? This is called simplified. Nothing else you can do? That shows you how we multiply rational expressions together. Make sure you always completely factor your numerators and denominators first, and then try to do any maybe cross canceling and or reducing, and you got it. Okay. You remembered multiplying rational expressions together in earlier algebra.
Yes.
Bringing back hopefully some good memories. It can be frustrating reviewing, ladies and gentlemen, what we've learned in the past. I'll tell you why, because reviewing things of the past, unfortunately, have you realizing how much you may have forgotten. And that's frustrating. Frustrating. That's our biggest enemy in mathematics, is we forget. We get rusty over time if we don't continue to use it. So it's a never-ending battle to keep this stuff fresh in your mind. And I remember when I was a student, if I did not have any classes between the winter semester and the following fall semester, I would literally take it upon myself to review a little bit throughout the summer and to keep it fresh in my mind. That way, when September rolled around, I hit the floor running, as opposed to having to start all over again from square one, which is no fun. So it's always wise to continually review a little bit if you can, ladies and gentlemen, if you can fit it into your schedule. It's only going to keep you sharp. Okay. All right, here we're going to try to divide some rational expressions. Do you remember how to do so in general? Do anybody remember the first thing we need to do here? I mean, the first thing, after the down, of course.
The reciprocal.
Yeah, we got to change division to multiplication and flip the second fraction upside down. We borrow that from basic math and how we divide whole numbers, okay, or fractions, excuse me, how we divide fractions. So we change division to multiplication, flip this thing upside down, take its reciprocal, rather. Now we're looking at this multiplication of these rational expressions here. All right. Now we got it down to this. And now we're back to, can we multiply some rational expressions together? And of course, to do so, we want to make sure we factor our numerators and denominators. when it comes to monomials, we just kind of leave them as is. I mean, we don't tear m to the 11th power apart into m times itself 11 times. You don't need to do that. That's called clutter on your paper. Can I factor m squared minus n squared? Anybody recognize it?
Yes, the difference of cubes.
No, not cubes, but
I mean square.
squares. So how would it factor?
M plus n and m minus n.
M minus n, you are correct. It factors into the product of these conjugate binomials. Now, unfortunately, this looks a little nastier, trying to factor this trinomial here. Is there anything I can factor out of all three terms first?
3.
Yeah, we can pull a 3 out. And ladies and gentlemen, when I factor a 3 out, that's all I can factor out. I'll leave behind what? 3m squared plus
2mn
2mn
minus 5n squared.
squared. And this all sits over our monomial of 18, m to the 9th, n to the 5th. But unfortunately, ladies and gentlemen, we got to ask ourselves, can this trinomial left behind inside the parentheses, can it itself be further factored down? Because if it can, we need to do so. That sure does not look like our normal trinomials because we have an extra variable present. We have n here and we have n squared here. But ladies and gentlemen, I'm going to drag this off to the side of my paper and show how we can factor this. Okay, it can be factored. We need to factor that down. So we're not done yet. All right. So let's do this here. We got 3m squared plus 2mn minus 5n squared. Let's try to use the grouping method on this, ladies and gentlemen. I know it doesn't seem like it's going to work, but it will. You'll see how. First of all, I'll take the product of 3 times negative 5 over here. And 3 times negative 5 gives me negative 15. I need 2 factors of negative 15 now that sum up to positive 2, the middle coefficient. Give me a couple factors of negative 15 that add up to 2. 5 and negative 3 are the only ones. Good. We're now going to rewrite this as an equivalent 4-term polynomial, so 3m squared, splitting up our middle term as the sum of our decided upon factors here. So 2mn is going to be rewritten as plus 5mn minus 3mn, mn. And now we're going to factor this by using what? Grouping, correct? Grouping. So here we go. We group together our first and last 2 terms. Careful how you group your last 2 together. You got a minus sign in front of your third term. I leave it outside the parentheses, so I must change the sign of the last term here. What can I factor out of the first 2 terms? Just an m, and I will leave behind 3m plus 5n minus, what can I factor out of these last 2 terms? N, that's it, n times, what do I leave behind? 3m plus just 5n, correct? Because n times n is n squared. N times n is n squared. Do you agree we got a common binomial factor shared by both terms? So we can factor out that common binomial factor, which is 3m plus 5n times, what do we leave behind in doing that? M
Minus
n, right? Everybody see how we factor that difficult trinomial, ladies and gentlemen, using the grouping method?
Yes.
Let's bring this factorization back to our main problem now. Bring this factorization back to our main problem. So I come back to my main problem and I replace this numerator right here with my factored form that I just accomplished on my scrap paper. Got to write this stuff down. Hold on, got to write all this down again. Okay, now replace this trinomial with its factored form, which is this right here. So this trinomial is now replaced with 3m plus 5n times m minus n. And this all sits over 18 m to the 9th, n to the 5th. Now that everything's factored, can we do any cross canceling here at all?
M minus N.
Yeah, the m minus n's drop out. They cross reduce out the ones. For now, that looks like about it. So if we bring this back together, multiply numerators together, what we have is we have 3m to the 11th n squared times this binomial 3m plus 5n. And that sits over the product of what's left downstairs, namely 18. I'm going to line up like bases, 18 m to the 9th, n to the 5th. All right, times what? M plus n, correct? This times this. Now, can we reduce this further? 3 over 18 reduces down to what? 1/6?
Yeah.
M to the 11th divided by m to the 9th is m to the 11th subtract 9, which is m squared. N to the 2nd divided by n to the 5th is n to the 2 minus 5 power, or n to the negative 3. So, ladies and gentlemen, we want to get rid of negative exponents. We don't want to leave negative exponents appearing in our final answer. So what has to be flipped?
N.
The n has to come downstairs. And so therefore our final answer is going to be m squared times quantity 3m plus 5n. And that's going to sit over 6n cubed. This comes downstairs times m plus n. And that is it. That's all you can do with this problem. Call it quits right there. Everybody see that there? That's it. Quite a problem, isn't it? Look at how long that problem is. And the longer a math problem goes, the greater chance there is for error. So be vigilant, ladies and gentlemen, and persevere to the end. Got to concentrate throughout your problems. There's so many areas to make a mistake here if we're not concentrating, okay? So many areas. That's your final answer. Any other questions about this problem here? Dividing rational expressions. Okay. How do we add or subtract rational expressions? Do you remember? Always comes back to can we remember? Never fails. Can we remember?
Do we have to have the same,
Yes.
Yeah.
Ladies and gentlemen, whenever you add or subtract any fractions, you always have to have a common denominator. That goes from basic math with whole numbers to now adding rational expressions together. You must still have a common denominator. Life is good here with this problem because we already have a common denominator. So no work necessary to get it. So all we do immediately is just add our numerators up and place that over your common denominator. Now, don't call it quits until you ask yourself if you can reduce. You need to ask yourself, can this rational expression be reduced? To entertain that possibility, we need to factor our trinomial numerator here. I need two factors of 10 that sum up to 7. What would they be?
2 and
times
5.
2 and 5. So this trinomial factors in n plus 2 times n plus 5, or you could have those switched around, divided by n plus 5. Now, what reduces out?
You can cancel out the n.
Yeah, these n plus 5s reduce to 1, leaving you with your final answer of n plus 2, and that is your final answer. That was a nice problem because we already had a common denominator. Unfortunately, we're not always going to have that luxury, ladies and gentlemen, of having a common denominator. We're not always going to have that luxury. And so we better get the problems that are more realistic. Let's see if we can subtract these rational expressions here. Let's try to take 4 over m minus 2 and subtract off 3 over m. Unlike the last problem, we do not have a common denominator here. So first thing we need to do is get one. So what would be the least common denominator of m and m minus 2? We need an expression for our least common denominator that's going to be divisible by both m and m minus 2. Being the case, our LCD better have an m in it, and it better have this binomial factor of m minus 2. This would be your least common denominator. Do you agree? Of both these denominators. Now we're going to have to build these fractions up into what are called equivalent fractions, where both denominators have to become what? The least common denominator. What am I going to multiply the first denominator by to build it up to my LCD? I already got the m minus 2. I'm missing the what? M?
Yeah.
Because of that, the first fraction, top and bottom, must get multiplied by m, here and here. This fraction or a rational expression is equivalent to our original first one. These are equivalent rational expressions. What do I multiply this for in the second denominator by to build it up to the LCD?
M-2.
M-2, top and bottom must get multiplied by M-2 to build it up to into an equivalent rational expression that now has the least common denominator. Now that we have a common denominator, we can begin to operate on our numerators here. So therefore, we'll have 4M distributing. Look at, careful here. We're not just going to distribute a 3 in here. We're going to distribute what kind of a 3?
Negative.
Negative 3. Don't mess these signs up. So that's going to be minus 3M plus 6. And this will sit over, you guessed it, our common denominator. Numerator, combining like terms, 4M minus M, 3M rather, is M. So we have M plus 6, and that sits over your common denominator. Ladies and gentlemen, notice you cannot do any reducing here, and so we are done. That would be your final difference between those rational expressions. That is simplified too. Does that problem make sense there? How we had to get a common denominator and build our fractions up into equivalent fractions. You remember doing that? And then take care of business. So you got to have a common denominator before you can actually add or subtract rational expressions together. Okay. All right. Okay, let's see here. Now, 2x minus 1. I want to show you this one. This one's a little bit tricky. Initially, it looks like these denominators are not the same, correct? As we strive to add these rational expressions together. But we can tweak this second denominator here and make it look identical to the first one. But how do we do that? Algebraically, how do we legally manipulate it? Well, ladies and gentlemen, here's what we can do here. Remember, you can
Multiply
always,
by -1.
yeah, or you can always factor 1 or -1 out of any polynomial. Do you agree? Those are like the trivial factors. You can always do that. Well, this is a time and place when you want to do that. Let's factor a -1 out of both these terms of the denominator. When we do that, we'll be left with -7 plus x. Isn't that true? Now, why did I do that? Well, why did I do that? Because you'll see now, ladies and gentlemen, that look at when I got plus and a negative. A plus and negative combined to give you just what? A minus. Everybody see that there? Plus and the minus, -1 factor. I'm combining them into a minus. Now look at my denominator of my second rational expression. You agree -7 plus x, if you spin these terms around, is the same thing as x minus 7?
Yeah.
Aha. Now we got a common denominator. So now we can take 2x minus 1 and subtract off the other numerator, x plus 6. Make sure you enclose it inside parentheses over x minus 7. And then we go from here. Distribute the negative sign inside the parentheses. We'll have 2x minus 1 minus x minus 6. Combining like terms on top. 2x minus 1x is what? X. -1 minus 6 is -7. What happens to the x minus 7s now? They reduce. What's our answer?
1.
+1. It simplifies all the way down to +1. Everybody see how we took care of that problem there?
1 minute. Just trying to write it down.
These are okay, they look very similar. And for that reason, by factoring -1 out of the last denominator here, you can make it look like the first, make it become identically the first denominator. All right, so a little manipulation with the factor of -1 there.
Okay, so I guess I'm kind of confused a little bit at that.
So I factored -1 out of both terms here. And there it is. And it leaves behind this.
Okay.
Now subtract, adding a negative, because you agree this -1 factor down here, when you got a -1 factor in the denominator of a fraction, you agree you can bring it outside the fraction? Do you buy that? Still the same thing, isn't it? So this negative sign can be brought outside the fraction. So adding a negative is the same thing as just what? Minusing off. Do you agree? Minusing off. Adding a negative combined to just give me a minus. Okay, do we have that one accounted for, everybody, one way or another?
Yes.
Are we good on that one? Good. As always, we're fighting the clock. There's so much to talk about, so little time. Ladies and gentlemen, why is this radical expression not simplified? Anybody? Why is that not considered to be simplified?
Because it's a square.
Because we have appearing in our denominator of our fraction a square root. We don't like to leave radicals in the denominator of a fraction. So do you remember how to simplify this? Anybody? How do we get rid of the square root downstairs?
Well, the X out.
Well, what we're going to do is we're going to multiply the top and bottom of this fraction by the square root of x. This is called rationalizing the denominator. When we do that, what's 7 times the square root of x? 7 square root of x? What's the square root of x times itself? Square root of x times x, or the square root of x squared? What happens to the square root now downstairs? What is this simplified to?
X.
Just x. The square root's gone. We have effectively rationalized our denominator. We went from an irrational denominator where we have the square root to a rational denominator. You remember doing that, rationalizing the denominator to get rid of a radical in your denominator? Have you ever done that before?
Yes.
All right, so what happens when you have this? 12 over the square root of 6 minus the square root of 2. This is not simplified because we got square roots everywhere downstairs. We got to knock both these square roots out here. Got to get rid of them, both of them. Anybody remember the magic bullet for knocking out both these square roots here?
You subtract them first.
What's that?
You subtract it first.
No, don't. No, you can't subtract square root of 2 from square root of 6. You can't even combine these. These are not like radicals. Okay. The word I'm looking for starts with the letter C. It's called, we need to involve ourselves with what's called the what of the denominator,
Conjugate.
the conjugate. The only way we're going to make both these square roots go away downstairs, ladies and gentlemen, is what we have to do is we have to multiply top and bottom of this fractional expression by the conjugate of the denominator. And the conjugate of the square root of 6 minus 2 is the square root of 6 plus 2. That's the only thing that's going to work. Now, the numerator, when you distribute the 12 in here, you're going to have 12 times the square root of 6 plus 12 times the square root of 2. Downstairs, ladies and gentlemen, when you're multiplying conjugates together, do you agree when you're multiplying like a minus b times a plus b, what's the product always going to be? Do you remember? Conjugates.
Cancel each other, right? No.
Well, remember, this always gives you the difference between the squares of the terms. Isn't that true?
Yes.
Isn't that true?
Yeah.
So, ladies and gentlemen, when we multiply these conjugate denominators together, it's just a matter of squaring the first term minus and squaring the last term. That's it. So therefore, this simplifies into 12 times the square root of 6 plus 12 times the square root of 2 over what? What's the square of the square root of 6? Just what rational number? Just 6. And the square of the square root of 2 is just 2. Look at how we got rid of all the square roots downstairs. We've rationalized the denominator. So we're left with 12 square root of 6 plus 12 square root of 6. 12 square root of 2, excuse me. All over what, 4?
Mm-hmm.
One last step you can do now is you can split this up and place both these over what, 4, and then reduce both of these. Legal to do this. 4 divides into 12. In each case, what, 3 times? And that would be our final answer, ladies and gentlemen. 3 square root of 6 plus 3 square root of 2. So the conjugate is what enabled me to rationalize this denominator and get rid of both those square roots down here. Had to multiply top and bottom by the conjugate. Does that ring a bell? Make sense, ladies and gentlemen? Any sense at all?
I mean, I see how you got it, but I'm just.
All right, Tony, does that make any sense?
Yes.
Okay. There's times when I can hear you, but there's times when I cannot make out what's going on. All right, so we covered covered.
Could
What's that?
I actually see the very end of that again? real
Okay.
quick?
Right down there. Okay. Right there.
Thank you.
All right, we covered a lot of ground here today. I mean, a lot of review, tons of review here. I mean, we've just basically spanned several chapters of intermediate algebra in the short time that we had together here today. We just spanned several chapters. It's amazing amount of material we covered in just the time we had. I'm going to leave you with one last problem, ladies and gentlemen. Doesn't look like we're going to get to a classwork number 2. Doggone it, we can never seem to get that second classwork in. Anyways, do you remember how to simplify one like this? How would we even simplify something like this? Well, all these negative exponents are a mess. Let's get rid of them. 2 times 8 to the negative 1 power would be 2 over 8 to the first power. B to the negative 1 power is 1 over B. See how I'm getting rid of all the negative exponents? 4 times a to the negative 2 power is 4 over a to the positive 2 power. B to the negative 2 power is 1 over b squared. In essence, we have what is called what? What do we call this construct? Anybody remember the name of this type of fraction? It's called a complex fraction. You ever remember simplifying complex fractions, ladies and gentlemen? Have you ever seen a complex fraction before in the past?
Yes.
Where you got fractions over fractions? The quickest way to simplifying this complex fraction is to find the least common denominator of all your denominators. And what would that be for a, b, a squared, and b squared? What do you think it's going to be? Well, we're going to need a squared. And we're going to need what? B squared. You see, when you're trying to find the least common denominator when it comes to variables, you choose the greatest exponent. I know it sounds like a paradox. When you're finding the greatest common factor of variables, you choose the least exponent. It's always the opposite. So we need a squared and we need b squared. So what would we do now? What we would do now is we'd multiply top and bottom of this thing by a squared b squared. This a squared b squared, when it gets multiplied into the first fraction here, you're going to have 2 over a times a squared b squared. Minus, when you multiply 1 over b by your least common denominator, you're going to have 1 over b times a squared b squared. Distribute the a squared b squared into both these fractions downstairs here. You have 4a squared times a squared b squared. Minus, you'll have 1 over b squared times a squared b squared. Now through cross canceling, we're going to get rid of all of our fractions. What happens to this a here? This a divides into itself once and takes out one of these a's, and you're left with a left over. So you're going to have 2ab squared minus this b divides into itself once, takes out one of these b's, leaving only a b behind. So we have minus a squared b. Fraction gone. Over. What happens to these a squareds? They cross cancel out, leaving you with 4 times b squared. B squareds cross cancel out, leaving you with just minus a squared. One last thing in the numerator, we can factor out a what? A 2ab, and we leave behind just what? B minus a. Wait a minute. You can't factor a 2 out. I'm sorry. All we can factor out in the numerator up here is just what? An a and a b. And what would we leave behind? 2b minus a. Downstairs, we have the difference between squares. So this can be factored into 2b minus a times 2b plus a. Difference of squares. The 2b minus a's drop, leaving you with your final answer, which is going to be what? What is my final answer here? AB over what?
2b plus a.
2b plus a. That's it. We're done with that problem. So we have taken, ladies and gentlemen, this, we wrote it so it's a complex fraction, got rid of all the fractions in our complex fraction by multiplying top and bottom by the least common denominator of all your denominators. Through cross canceling, it simplifies down to a simple rational expression that can then be reduced via factoring the numerator and denominator. And you're left with that. All right. Unfortunately, there is just not enough time for our classwork number 2. So what are you going to send me by midnight? Only classwork 1?
Yes.
Those 4 problems? All right. Please get those to me. Make sure, again, you put math 130 in the subject line, ladies and gentlemen. That's very important. So it gets routed to the correct folder. Otherwise, I may never, ever find that message. Okay. You guys have a great day. I'll be on the line for a couple minutes if you have any questions or concerns. All right. I already posted the next textbook homework assignment for you on Canvas. All right. Take care. See you Wednesday, hopefully.
Have a good day.
Yeah, you too. Have a good one.
Did you get the last homework assignment I emailed?
The last homework assignment?
Yeah, did you get it?
Yeah, I think I got it. But again, don't email me your textbook homework assignment until I issue the first exam, okay? Which won't be till what, October like 20th or something, all right? Just hang on to your homework, okay, Tony?
I should say the classwork, but I didn't email.
Oh, the classwork. Yes, I did receive your classwork. Mhm.
Okay.
I still have to record the classwork though.
You say you don't want us to send a homework assignment?
I'm sorry. Again, it's very, very faint. I can barely hear you. What'd you say?
You say you don't want us.
You know, maybe if you type me a chat message, Tony, that might be better. You know how to just type a chat message? Send me a chat, Tony.
This is just a quick question, but I know that you're recording these. Do you upload